Welcome back once again. Now let us see the alpha decay. Students, as we have learned in case of binding energy per nucleon, what we have learned there? The element whose mass number is greater than 170, for those elements, binding energy per nucleon is very small and are unstable, and they act as a radioactive elements. From those elements, continuously or spontaneously, the nucleus will be disintegrated by emitting certain types of radiations. One of the radiation emitted during the nuclear disintegration, that is happening alpha decay. Right? This alpha decay is a nuclear phenomenon. See here, during the alpha decay, the original nucleus is converted into another nucleus. Along with the large amount of energy will be released. Along with large amount of energy will be released. Here, what is alpha decay? Alpha decay is the process of emission of helium nucleus during nuclear disintegration. During nuclear disintegration, the helium nucleus is emitted during this process that we are calling. First of all, I will take a radioactive substance. Look at it. This is the radioactive substance. This is the nucleus. This atom is represented by the nucleus by mass number A and atomic number C. Right? From this nucleus, if an alpha particles are emitted, are emitted. In alpha particles are emitted, this original nucleus is converted into new nucleus. Original nucleus is converted into new nucleus along with large amount of energy. See here, during the alpha decay, the original nucleus is converted into new nucleus. The original nucleus we are calling parent nucleus, and the converted nucleus we are calling daughter nucleus. See here how this process is possible. The process of emission of the alpha particle. Actually, this alpha particle is a helium nucleus. See here. So shall we take this we are calling parent nucleus. When this parent nucleus emits the alpha particle, it converted into new nucleus. Converted into new nucleus plus helium along with the large amount of energy. When alpha decay occurs, the mass number of parent nuclei is decreased by 4 units and atomic number is decreased by 2 units. Right? Shall I take example? For example, I will take uranium-238. It is a parent nucleus. This parent nucleus has a mass number 238, atomic number is 92. When this parent nuclei emit the alpha particle, this converted into new nucleus plus helium along with large amount of energy. During alpha decay, mass number decreased by 4 units. 4 unit means 238 becomes 234 and atomic number decreased by 2 unit. 92 becomes 90. Right? We say that during the alpha decay, a helium nucleus is emitted. Helium nucleus is emitted along with a large amount of energy. See here, this we are calling reactant and this we are calling products. In case of nuclear disintegration, that is during the emission of alpha particle or beta particle, the masses of the reactant always greater than masses of product. What it is? The masses of these reactants are always greater than masses of product. Due to difference in mass, the energy will be created. That energy we are calling Q value of energy. This energy energy we are calling Q value or disintegration energy of nuclear phenomena. What about this energy? Due to difference in masses of product and reactant, that mass is converted into energy. That energy we are calling Q value of energy or disintegration energy of nuclear process. See here, how to define this Q value of energy or disintegration energy? This disintegration energy is the difference in mass energy of a reactant and product. Difference in mass energy of reactant and product. For example, see here, the masses of this reactant can be represented by mx. The masses of this product, what product? Y, that is My, and masses of the helium can be represented by M. So similarly for this one, this we are taking mx, this we are taking My, and this we are taking what value? M. This is masses of reactant and these are what? Masses of product. What we say? The masses of product are always less than masses of reactant. Due to the difference in mass, energy will be applied. That we are calling Q value of energy or disintegration energy. Then this disintegration energy or Q value of energy how to define? Q value of energy is the difference in mass energy of reactant and product. Difference in mass energy of reactant and product. This Q value of energy that can be given according to Einstein mass energy relation. Einstein mass energy relation, where M indicates what? Difference in masses of reactant and product. How to take? See here, this E can be represented by Q value. E can be represented by Q value. This Q value M, what is M? Difference in masses of reactant and product. How to take? The difference in masses of reactant and the product. This we are calling Q value of energy. Then in terms of AMU, how to represent? In terms of AMU, this energy can be represented. Energy can be represented mx minus of how much? This is what My, sorry. This is My and this is what? M. Right? My minus of what value? M alpha into what value? U mean in terms of atomic mass unit. But 1 AM equal to 931 mega electron volt. How to represent? See here, Q equal to what? Q equal to mx minus of what value? My into M alpha. U equal to what? 931 mega electron volt. Right? I mean, when alpha particles are emitted from nucleus, this much amount of energy will be released, and the amount of energy released during the alpha decay is equal to the sum of kinetic energy of a daughter nucleus and helium nucleus. Directly, the Q value of energy is the sum of kinetic energy of the daughter nucleus and the helium nucleus. Following? See what it is? The Q value of energy during alpha decay is the sum of kinetic energy of a daughter nucleus, Y nucleus, plus kinetic energy of alpha particle. I mean, this energy is saved by the daughter nuclei and the helium nucleus. And remember, this Q value of energy is always positive. Always positive for alpha decay or beta decay, because the masses of product are always less than masses of reactant. Masses of this product always less than masses of reactants, and this Q value of energy will be positive. If Q value of energy will be positive, this process we are calling spontaneous process, and the reaction will be exothermic reaction. For exothermic reaction, this Q value always positive, and the process must be spontaneous. That's what this alpha decay what we are calling spontaneous process. Students, what we made here, during alpha decay, mass number decreased by 4 units, atomic number decreased by 2 units, along with helium nucleus with large amount of energy. See here, this emitted helium nucleus, how much it has the charge? Actually, how to represent the helium nucleus? Helium nucleus is nothing but alpha particle. It is a alpha particle. This helium nucleus has a charge. That the charge must be equal to charge on proton. What is the charge on proton? The charge on proton equal to 1.6 into 10 raised to minus 10. Fine. It has the mass number. The mass number of the helium nucleus must be equal to 4 times the proton. What it is? The mass number must be equal to 4 times the proton of the helium nucleus. The proton mass is there 1.6748 into 10 raised to minus 27 kg. See here, what mass is available? Mass of the proton equal to 1.626 into 10 raised to how much? Minus 27 kg. See here. The emitted helium nucleus has a kinetic energy. The kinetic energy of helium nucleus is very small. And see here, the kinetic energy of helium nucleus can be calculated by one formula. The formula directly I will use. The kinetic energy of the helium nucleus can be represented by the formula. That formula can be given A minus 4 divided by A into Q value. What is A? A represents mass number. Mass number of parent nucleus. Or directly A minus 4 is nothing but mass number of daughter nucleus. Mass number of daughter nucleus divided by mass number of parent nucleus into Q value. This Q value can be given by this formula or by this formula. But when alpha particles are emitted, we said that the charge of the alpha particle must be equal to charge of the proton and mass must be equal to 4 times the mass of the proton. This emitted alpha particle has some of the properties generally. See here, this alpha particle is a positively charged particle. Due to positively charged particle, these alpha rays, they can deflect by electric field and magnetic field. Due to charging particle, this alpha particle or helium nucleus, it can be deflected by electric field and magnetic field. This is one of the properties of alpha rays. And second property can say, this alpha particle can affect the photographic plate. They can affect the photographic plate and that can cause fluorescence. One thing. This alpha rays has a low penetrating power because this alpha rays having less amount of kinetic energy. Due to lesser kinetic energy, they have low penetrating power and they have strong ionizing power. They can ionize. They can ionize because they are having the more masses. That is, mass of the proton, mass of the helium nucleus is equal to 4 times of mass of the proton. These are what? Few properties of alpha rays. I mean, alpha rays, they are the positively charged particle. They can deflect by electric and magnetic field. They can cause fluorescence. They can affect the photographic plate. And generally, they have low penetrating power along with the high ionizing power. This is what regarding alpha decay. But now we have to see the one more decay that we are calling beta decay. Beta decay. Beta decay. See here, the unstable nuclei whose mass number greater than 170, they can emit the radiations. So one of the type of radiation emitted from the radioactive nuclei is nothing but the beta decay. Students, already we know that inside the nucleus only protons are there and neutrons are there. inside the nucleus, the proton may not remain the proton and neutron may not remain the neutron. Instead, for stability of the nucleus, the proton is converted into neutron and neutron is converted into proton. During interconversion, they emit some type of radiation that we are calling beta decay. The beta decay is the process of emission of electron or positron during nuclear disintegration. What it is? The process of emission of electron or positron during the nuclear disintegration. That we are calling beta decay. Then how to say inside the nucleus only protons are there, neutrons are there. Then how it is possible to emit an electron from the nucleus? This is interesting factor. Interesting factor is during conversion of proton into neutron and neutron into proton, the emit either electron or positron. During the emission of electron or positron, the beta decay we can classify into two categories. One is positive beta decay and next one is negative beta decay. Remember students, during beta decay, the mass number of a daughter nuclei that remains same, but atomic number will be rise by 1 unit or falls by 1 unit. So let us see clearly. When positron will emit during nuclear disintegration, when electron will emit during nuclear disintegration. So first of all we will see negative beta decay. Negative beta decay. Negative beta decay. Negative beta decay. Negative beta decay is the process of emission of electron during nuclear disintegration. Process of emission of electron during nuclear disintegration. See here. First of all, I will take a radioactive nuclei. This is the radioactive nuclei. So, nucleus can be represented by mass number A and atomic number C. Right? When this nuclei emit the negative beta decay, the original nucleus that we are calling parent nucleus, the parent nucleus can be converted into another nuclei. That nuclei we are calling daughter nuclei. For this daughter nuclei, the mass number remains same. Mass number remains same, but atomic number will be increased by 1 by. Atomic number will be increased by 1 by along with the large amount of energy. What we said? The process of emission of electron during nuclear disintegration, that we are calling negative beta decay. During negative beta decay, it emits electron. During emission of electron, the parent nuclei converted to daughter nuclei. For this daughter nuclei, mass number remains same as compared to parent nuclei, and atomic number will be increased by 1 by along with the large amount of energy. Right? Then how to represent the equation? See here. This is the parent nuclei. If it emits electron or negative beta decay, it converted into new nucleus. During new nucleus, mass number remains same, but atomic number will be increased by 1 value along with the large amount of energy. Right? That is negative beta decay occurs. When it occurs, inside the nucleus, the neutron is converted into proton. During neutron is converted into proton, it emits the electron. I mean, see here, if it is neutron, inside the nucleus, the neutron is converted into proton. During interconversion, the neutron is converted into proton, it emits the electron. It emits the electron along with This we are calling what? Electron. How the electron will be? During interconversion of neutron into proton, it emits an electron along with some subatomic particle. This particle we are calling antineutrino. Then how to give the example here? See here. Example for this negativity charge is, I will take PP like 210. What about this? 82. Right? When this will be converted, this is parent nuclear. This becomes daughter nuclear this month. Right? For this 210 mass number I can say the atomic number will be increased by 1 unit along with large amount of energy. So first of all, let us see what about the energy during negative beta decay. During negative beta decay, energy will be emitted. The energy will be emitted because of the masses of the reactant are always greater than masses of product. Due to difference in masses of energy, mass energy of reactant and product, the difference in mass will be converted into energy. Again, this energy can be given equal to mc square formula. That is difference in masses of reactant minus product into c square. That is nothing but what? Q value of the energy. Then now let us see. When neutron is converted into proton, it emits the electron. This electron we are calling beta decay. Negative beta decay. Along with some subatomic particle that we are calling antineutrino. So we will discuss about the antineutrino later. Remember, negative beta decay means the process of emission of electron from the nucleus during nuclear disintegration. That we are calling negative beta decay. Now let us take positive beta decay. Positive beta decay. Positive beta decay. Positive beta decay. See here. During interconversion of proton into neutron, a positron will emit. Positron will emit. See here, what happens? In case of negative beta decay, during the interconversion of neutron into proton, electron is emitted. Electron is emitted. This electron has the charge already, one mass already. Charge will be replaced by 1.6 into 10 raised to minus 19 coulomb. And mass will be replaced by 9.1 into 10 raised to minus 32 kg. So let us take what happens here. Positive beta decay. Okay, what is positive beta decay? The process of emission of positron during the nuclear disintegration. That we are calling positive beta decay. See here, what happens? Again I will take, this is the parent nucleus, represented by the mass number A, atomic number Z. When this nucleus emits the positive beta decay, the parent nucleus that will convert into daughter nucleus. During daughter nucleus, mass number remains same, but atomic number will be false by 1 unit, along with the large amount of energy. Along with the large amount of energy. Equationally, how to derive? Equationally, this is the parent nucleus. This will be converted into daughter nuclei. Atomic number remains same, and the mass number will be increased by 1 value, along with large amount of energy. This is what? During the positive beta decay. Here what happens? Atomic number of the parent nucleus decreased by 1 value. That we are calling daughter nucleus, but mass number remains same. You can take the example. For example, for sodium. Sodium has the mass number 22, atomic number 10. This parent nuclei converted into daughter nuclei during positive beta decay. See here. During positive beta decay. Sodium becomes neon. Your mass number remains same, but atomic number will be decreased by 1 value, along with large amount of energy. Again, this energy can be given difference in masses of reactant and product. The mass energy of difference in mass energy of reactant and product that we are calling Q value. Right? But how the positron will emit. See here, when proton is converted into neutron inside the nucleus, the proton is converted into neutron inside the nucleus. During the interconversion, it emits a positron plus some subatomic particle. During interconversion of proton into neutron, it emits the positron, where positron is an antiparticle of electron. Positron is an antiparticle of electron. Difference is the mass of the positron must be equal to mass of the electron, but charge will be difference. If the charge of the electron is minus 1.6 into 10 raised to minus 15 coulomb, but charge of the proton is plus 1.6 into 10 raised to minus 15 coulomb. And what about this particle? This particle we are calling neutrino. How neutrino produce? Neutrino produce during interconversion of proton into neutron along with the positron plus neutrino. Actually, this neutrino, it is an atomic subparticle. Almost this neutrino has a chargeless particle and nearly its mass may be zero. Nearly its mass may be zero. Due to weak interaction with matter, this neutrino, it is very impossible to detect because low interaction with the matter. But remember, this subatomic particle neutrino, it has a high penetrating power. Without interaction, it can easily go into the body. Even inside the earth it can go. Without interaction, it has high penetrating power with the matter. Actually, what I said, neutrino is a subatomic particle, almost a zero charge, almost neutral particle, and zero mass. Weak interaction with the matter, and they can easily penetrate with the matter. See here, during negative beta decay, antineutrino is produced. Actually, antineutrino is an antiparticle of neutron. Difference between neutrino and antineutrino. Neutrino has zero charge, but it has the charge. So directly, what you can say? During negative beta decay and positive beta decay, during negative beta decay, electrons are emitted, and during positive beta decay, positrons are emitted. During the both process here, what happens? Mass number remains same, but in the negative beta decay, mass number increases by atomic number increases by 1 unit, and during positive beta decay, atomic number will falls by 1 unit. Say, in both cases, the amount of energy will be released. Amount of energy will be released. The both energy can be calculated. The difference in mass energy of reactant and product according to Einstein mass energy relation. But remember this point, students. Either during alpha decay or beta decay. During alpha decay or beta decay, the daughter nuclei always it is in excited state. Always it is in excited state. When daughter nuclei is in excited state, it comes to ground state. When it comes to ground state, it emits one more particle. That particle we are calling gamma particle. Remember, in case of alpha particle, it has a properties. Similarly, this beta decay has some particles. Generally, beta decay is a negatively charged particle. It can deflect by electric and magnetic field. Right? It has less analytic power and low penetrating power as compared to alpha particle. Now let us see about the gamma decay. What we said? During alpha decay or beta decay, the daughter nuclei it is in excited state. The excited state of daughter nuclei comes to ground state by emitting certain types of photon. That photon we are calling gamma rays. I mean, after alpha decay and beta decay, the gamma decay will occur. But remember this point. At a time all three types of radiations are not emitted at a time. Alpha, beta or gamma decay not possible. First of all, either alpha particles are emitted, next maybe beta particles are emitted. After alpha particle and beta particle are emitted, gamma particles are emitted from a nuclear process. That we have to see. That we have to see about gamma decay. Gamma decay. Gamma decay. Students, first of all, like atom, nucleus also discrete value of energy levels, like ground state and excited state. After alpha decay or beta decay, the daughter nucleus, it is in excited state. When it comes to ground state, it emits certain types of radiation. The difference in atomic energy spacing and nuclear energy spacing. The atomic energy spacing, it is measured in terms of electron volt, but nuclear energy spacing, it is measured in terms of mega electron volt. Right? How gamma decay is possible? That we have to see. First of all, let us take nuclear energy states. Nuclear energy states. Shall I take? These are nuclear energy states. Nuclear energy states. Right. So it is the ground state. E naught. This we are calling first excited state. This we are calling second excited state. Right. First of all, let us take negative beta decay. Negative beta decay. For example, shall I take the example for negative beta decay? So I will take the lead 210. Atomic number will be represented by 82. When this nucleus emit the negative beta decay, negative beta decay, so this becomes this one. Right? So mass number remains same, atomic number will be increased by 1 along with large amount of energy. This parent nuclei emitted the daughter nuclei. This daughter nuclei is in excited state. How to represent in this figure? See here. This we are calling what? Parent nuclei. Mass number to 10, atomic number will be 82. When it having negative beta decay, when this will be having a negative beta decay, this will be a negative beta decay. This becomes the daughter nuclei. Mass number to 10, atomic number will be 82. This daughter nuclei, it is in excited state. Excited state can be represented by this one. This excited state of a daughter nuclei comes to ground state. Comes to ground state by emitting certain types of radiation. That we are calling gamma decay. That we are calling gamma decay. This excited state of daughter nuclei comes to ground state by emitting a photon. This we are calling gamma decay. Gamma decay means the process of emission of photon. Process of emission of photon from radioactive nucleus. So when this daughter nuclei comes to a ground state, this becomes normal. That is 210 and this becomes 83. This gamma decay, the process of emission of photon during nuclear disintegration. That we are calling gamma decay. The emitted photon, gamma decay means photon. The emitted photon has the energy energy of the photon can be represented by this value, E is equal to h nu. And nu represent the frequency of emitted radiation. The energy of the photon equal to difference in the excited state and ground state. Excited state and ground state. This energy has corresponding wavelength and frequency. I mean, when the daughter nuclei comes to ground state, it emits certain types of radiation. That radiation we are calling gamma radiation. During gamma radiation, a photon emits. The photon energy can be given E is equal to h nu, and the energy will be equal to difference in energy of excited state and ground state. This emitted energy has certain types of wavelength and certain types of frequency. The frequency of the gamma radiation that must be equal to smaller than or equal to the wavelength of X-rays. Remember, this gamma decay is a neutral particle. It has no charge because photon has no charge. Due to neutral particle, this gamma is emitted from excited state that does not reflect by electric and magnetic field. But this gamma is emitted from excited state. They are having high penetrating power, but they have less ionization power. Ionizing power is less, but penetrating power is more as compared to alpha rays and beta rays during gamma decay. When this gamma rays incident on the metal surface, electrons are emitted. That effect we are calling photoelectric effect. That we will learn in the next chapter. I mean, when this photon of this energy E equal to h nu incident on the metal surface, electrons are emitted directly. The gamma rays are responsible for photoelectric effect due to E is equal to h nu has the energy. I mean, when gamma rays are emitted, followed by alpha decay and beta decay, gamma rays are emitted. The gamma rays are emitted due to excited state of a daughter nucleus. So this is corresponding to alpha decay, beta decay and gamma decay. So next we will see. Thank you.